All right, so we just introduced social preference utility functions. And this idea has really been a part of behavioral economics. And yet, Vernon Smith, kind of the founder of the experimental economics movement in the 20th century, has some kind of criticism about this and really feels that if we go back even further to the works of Adam Smith, we get a better understanding of human interaction than we do from these social preference utility functions, right? And so Vernon Smith has said utility was an imaginary construct about the subjective value. Whatever it was supposed to measure, you maximized it. But the attempt to identify consistent and reliable measures of utility have persistently failed. Vernon Smith thinks that understanding interaction and transactions when it comes to the ideas of cooperation, fairness, and trust are better understood by Adam Smith's model of man, looking at the sentiments from exchange and interaction, than by these modern neoclassical-esque social preference utility functions. We cannot identify some simple optimizing utility function. Instead, we exhibit what Vernon Smith calls an ecological rationality. The context matters. The norms and the violation of norms matter. These things create the environment within which we make decisions. We should appreciate man as having more depth to his rationality than simply an altruistic preferenced utility function or a Rawlsian utility function. Those stagnant approaches miss the point. Man is much more dynamic. Vernon Smith explores these ideas of trust within trust games and reciprocity emerging from interaction. And that's what we're going to look at next. So in the laboratory, Vernon Smith ran a bunch of games from standard game theory and kind of manipulated them a little bit to try and see how do people actually play. And so here we have a voluntary trust game, right? And so Vernon ran this with these payoffs, and he looked at, kind of what happened here. So this is a voluntary trust game. So in this game, what happens is that player A has the option to just kind of end the game right away and get this 10-10 payoff, where player A gets 10 and player B also gets 10. Or player A can kind of pass the game down to player B. And then player B gets to act, right? So at this point, player B gets to decide what to do. And the game is over after player B moves. So player B can just do this payoff down here where player A gets 0 and player B gets 40. Or player B can play over here where player A gets 15 and player B gets 25. Now, if this is standard game theory, the way that we go through and solve this is that we would say, okay, in this setting, we have a situation where player B, we have to use backward induction. Player B has the option between 25 and 40. Clearly, if we face this, player B is not going to choose the 25, and so we can just simply get rid of this element here. Player B would choose the option to play all the way down here and get this payoff of 40. And if player B has that, then we can move up to the kind of first level of action. We've solved the end of our backward induction. We can look at what player A would do, given that the options are 10-10 or 0-40, right? And player A is considering this payoff of 10 or 0. Player A is going to prefer 10 over 0. And so what we can do is say that player A would never play here. And so what we'll get is this 10-10 outcome, right? Now, we have this 10-10 outcome as the backward induction standard economic game theory solution, and yet it's clearly Pareto inferior to the 15-25 option, right? So with the 15-25 option, both players are made better off. And it's actually even worse in terms of total net to the 0-40 outcome, right? So we have a total payoff of 40 down there, and here we only have a total payoff of 20. And so, man, this is a really bad outcome that we have, and yet that is what our Nash play is within this standard trust game that we have. And yet, what do we see when Vernon Smith ran this game? Right, he sent some participants through it. What happened is that A passed about 50% of the time. So about 50% of the time, we just kind of ended the game, and about 50% of the time, they kind of played this cooperative approach where they passed it to player B, trusting that player B would do the right thing. Once player A passed it, right, so it's only 50% of the time that player A passes it, but once player A passes things along, what we ended up seeing is that about 3/4 of the player B right, end up cooperating. So 75% of the time, player B actually cooperates, whereas only 25% of the time do they kind of do the Nash play where they take the payoff of 40 over their payoff of 25, right? And so this is kind of our first setup here, the first kind of round of games that we want to think about. So this is our voluntary trust game. We're going to compare this and these results to a couple of little tweaks that we'll put in, and we'll see how Vernon Smith talks about these things, right? And so the first tweak that we're going to have is this involuntary trust game. So it's exactly the same as the trust game. However, player A doesn't voluntarily pass it to player B. There is no option for player A to come over here and get this 10-10, right? That doesn't exist. So player A just automatically passes it down to player B, and player B knows this. There's common knowledge here. All the other payoffs are exactly the same within this setting, right? In this situation, player B, what do? About 33% cooperate here, and about 67% just kind of go with the Nash play and take the larger payoff of 40, right? And so we get kind of a different outcome in this setting. The second tweak that we want to look at is just to look at slightly different payoffs and how this could skew the results as well, but the general tone still remains the same. So here we just have kind of tweaked payoffs from our original voluntary trust game. And this one is less extreme. There's slightly different payoffs and they're less extreme payoffs. Notice that player 1 doesn't get a 0 down here, as we're going through. And the big payoff isn't quite as big. It used to be 40, now it's only 30. So this is just a kind of less extreme game that we have here, right? So it's same basic setup though, the same kind of, end result is that we should end up with, through backward induction, player B would go here, which eliminates this option of them kind of cooperating, and then player A is going to choose between this 15 and the 20, and so they're going to eliminate this payoff, and so we end up with the same outcome here of kind of the A just ends the game right away according to Nash play. How do people actually play it? In Vernon's situation, what happened is he ran about 30 of these, so 27 of these, and what we end up with is kind of a different kind of outcome here, right, than in the first case. So what happened is that 10 out of 27 of player A's exited right away, right? So they just said, so 10 out of these 27 exited. So not quite 50%. So more player A's are passing on to player B here, right? So originally it was about 50-50. More people, player A's, are passing it on. And then B, what's happening to B is we have about 11 out of the 17 that got passed are actually then cooperating, right? And so we have a little bit different numbers here, and we'll analyze those that's happening, in terms of what's happening. But we're going to have this situation where player B is not cooperating as much. Player B is more likely to jump down here and take the 30 in this game, at least according to these experimental results. Right, so let's look at these results now then. And so we can first look at this voluntary game. This is our standard approach is over here. So this is our standard voluntary approach, right? And then this is our first tweak, which was the involuntary approach, right? So we're comparing these two kind of experimental results, right? And so we already kind of said the numbers here, but in the first game, the voluntary approach, we had the 50-50 split and then a 75% cooperated, right? So how do you create a standard social preferences function in this situation when B's options do not change and yet his behavior does? If you're just going to look at player B, how do you create a social preferences utility function that says, oh, okay, yeah, when you're facing these two choices, in this case, 75% of the time you're going to do this, and in this case, only 33% of the time you're going to do this, right? What's happening here, right? How do we have like a altruistic or Rawlsian utility function here to kind of represent this? We can't, right? Instead, what we have to do is we have to look at the game as having been kind of this sequential game that revealed some information, and part of the game creates a context and changes the player's behaviors. We don't just have a stagnant utility function that can tell us what player B is actually going to do, right? In this situation, player A never showed any trust in this game. Player A was forced to pass it on to player B. Whereas in this game, player A actually, the Nash play is just to go over here, and they might lose pretty big if they pass it on to player B, and yet they showed some trust when they passed it down to here, and that trust was reciprocated by player B, right, cooperating along with player A more often. Right? Whereas here, not, in this situation over here where it's in the involuntary game, not much trust was, shown here by player A moving it down to player B. In fact, none. He was forced to do this. And so player B feels less concerned about reciprocating that trust, right? And so we can see kind of these kind of weird payoffs happening here with player B because player A showed some trust in the first place. Now, if we look at this tweak of the voluntary payoff, but with the less extreme payoff. So here we have our original voluntary setup again in the experimental results that Vernon Smith got. And now we have the voluntary, but with, less extreme payoffs, right? And so this was our second tweak here on this side here, right? So we have this voluntary payoffs, but with this less extreme payoffs. And we can look at what happens in this game compared to the voluntary game as well, right? So in this game, what happens, right? In the first game, this is a lot riskier, right? The move for player A to pass things along is a lot riskier in this second game than it is in the first game. In the first game, they could end up with a 0. And so there's quite a bit of risk there in that situation. The second game, it's less extreme. You could only drop by about 25% if you pass things along. So you could go from 20 down to 15, right? So it's less of a drop and you're still getting a payoff of 15. When Vernon ran this second game, he saw that, we have a situation where the second player behaves differently again, right? 75% of the player Bs cooperate in this first case, and a bit under 65% cooperate in this second case. Well, why would this be? Again, we have to look at the fact that we as humans are reciprocators. How much trust did player 1 really show in this less extreme case? Did player 1, by moving down here, showcase a lot of trust? The answer is no, not really, because all they were going to lose was a little bit, and maybe they get something, right? And so there wasn't a whole lot of trust in this pass to player B. So that move where A goes down to player B, that didn't showcase a whole lot of trust, right? As a result, player B is more likely to defect and play this down where they get this bigger payoff in this case than they are in the first case where player A showcased a lot of trust, right? When player A doesn't show all that much trust, player B is much more willing to do this defection here and get this kind of big payoff for themselves. And now this is true even though the gain is much smaller for player B. Note, the defection is just a move from 25 to 30 for player B, whereas in the first case with the more extreme payoffs, the defection jumps them from 25 to 40. So the defection by player B seems like it would happen more often in the first case, and yet it happens less often, right? We would think that this change from 25 to 40 would cause player B to go in that direction more often, and yet we get more of player B's in this second situation actually playing that defection within that setup. All right, so there we had Vernon Smith using experimental evidence to kind of critique some of these social preference utility functions from behavioral economics. But up next, we'll try and bring all of this together and bring to a conclusion our lecture on trust, cooperation, and fairness.